Welcome to this explainer. Today, we're diving into the invisible world of radio frequency connectivity. You know, it's a space that absolutely relies on uncompromising physical precision to keep our modern digital lives running. Think about it. Every single time you stream a video, make a call, or connect to a network, you're leaning on physical components that just have to perform flawlessly under immense electrical stress. So let's jump straight into this catalog from Vitalconn. And I don't want us to treat this like just some boring list of parts, right? Let's look at it as a masterclass in high-frequency engineering. This document literally outlines how engineers design physical components to eliminate signal interference. It's an absolutely fascinating look at the actual hardware making our entire wireless world possible. Just to make sure we don't get totally overwhelmed by all the technical specs, here's our visual roadmap for today's spec teardown. We're going to hit 1. Defining excellence. 2. The test adapter lineup. 3. Anatomy of a connector. 4. Precision cable assemblies. And finally, 5. The low PIM advantage. All right, starting off with Section 1, Defining Excellence, Navigating the Catalog. Let's look at the big picture and see exactly how Vitalconn organizes these fundamental building blocks of telecom networks. Looking at this cleanly structured index, it takes what could honestly be a totally confusing alphabet soup of part numbers and categorizes them into super logical solutions. We've got test RF adapters for seamless component bridging, solderless RF connectors for rapid deployment, and test cable assemblies to bridge longer physical distances without dropping the signal. It's really all about categorizing the right tools for high-frequency testing and total signal stability. Moving right along to Section 2, the test adapter lineup, standardizing precision. Now, let's zoom in specifically on those test adapters and check out the baseline metrics you need for industry-grade reliability. Across this entire lineup, you're going to notice a relentless, almost obsessive level of consistency. Specifically, take a look at this universal 50-ohm characteristic impedance. Now, in the RF world, 50 ohms is literally the gold standard. It perfectly balances power handling capacity with minimal signal loss. You'll also see these adapters operating across a huge frequency range, all the way up to 6 GHz, while maintaining a VSWR of less than or equal to 1.15. And honestly, this brilliantly illustrates what VSWR, or voltage standing wave ratio, actually means in the real world. Think of it like water flowing perfectly through a sealed pipe. A VSWR of 1.15 basically means the connection is so seamless that almost zero energy splashes back toward the source. It ensures your signal doesn't degrade as it passes from component to component. It's just maximum efficiency. That brings us to Section 3, Anatomy of a Connector, Mathematical Blueprints to Physical Reality. Let's look at the physical parts themselves and see how these mathematical ideals actually get manufactured. What's really cool here is the stark contrast between theory and execution. On one side, you've got the theoretical, mathematical blueprint of an SMA adapter. We're talking exact measurements down to fractions of a millimeter. And on the other, you see the beautifully machined brass and copper reality, taking those exact schematic tolerances and translating them into physical metal that perfectly mates with another component. That is just an incredible feat of modern machining. Now, to survive extreme electrical stress, these tiny adapters boast a remarkable 500-volt dielectric withstanding threshold. How on earth do they handle that much power in such a tiny physical footprint? Well, it all comes down to integrating highly resilient materials. The internal contacts are forged from beryllium copper for superior conductivity, and they're surrounded by PTFE, which acts as an absolutely incredible insulator against electrical arcing. Even as the physical geometries get way more intricate, like with the ESNP Max adapter, the standards just do not slip. Notice the grooved texturing on the blueprint and then on the actual part. Despite this highly complex shape, that same extreme 500-volt durability and that crucial sub 1.15 VSWR remain flawlessly intact. It completely proves that form can get more complex without sacrificing even a drop of function. All right, Section 4, Precision Cable Assemblies, Connecting the Pieces. Stepping back out to the macro level for a second, we really need to look at how these tiny, perfect adapters are successfully linked across greater physical distances. The catalog smartly groups its heavily shielded cable assemblies into 3 main performance tiers: millimeter wave, VSWR, and low PIM. Each one of these is engineered with a very specific operational environment in mind, but they all share one absolutely critical goal: to aggressively protect fragile high-frequency signals as they actually traverse the physical space of the network.
As we scale up to thicker cables using the larger N-type connectors, the engineering scales right along with it. The power threshold here skyrockets to a massive 1,500 volts of dielectric withstanding capacity. So we aren't just talking about delicate lab instruments anymore. This is heavy-duty infrastructure, purpose-built to push massive amounts of data and power without breaking down. Which leads us perfectly into Section 5, the low PIM advantage, eliminating interference. You see, the crucial point in modern networks isn't just about carrying heavy power over cables. It's really about keeping the background completely silent. Which brings us to PIM.
So PIM, or passive intermodulation, is essentially high-tech signal noise. When multiple high-power frequencies mix together inside a physical component that isn't perfectly linear, maybe because of a microscopic surface defect or even just the wrong metal, it creates these unwanted ghost signals. And those ghost signals absolutely wreck cellular network capacity. To combat this, Vitalconn uses specialized materials like phosphor bronze and exact machining to suppress those rogue frequencies entirely.
Just look at this heavy-duty RG401 cable assembly, for example. It achieves a third-order intermodulation score of less than -168 decibels. In the engineering world, that represents a nearly perfectly silent connection. Achieving that level of absolute silence while simultaneously handling a jaw-dropping 2,000 volts of dielectric withstanding power, that is just a stunning engineering achievement. It's literally the pinnacle of clean power delivery. As our global data demands continue to explode, driven by 5G, IoT, and whatever comes next, it really leaves you wondering. We talk a lot about software, the cloud, and AI, but just how much of our entire digital infrastructure completely depends on the unseen physical perfection of these vital, meticulously machined metal components? Without them, the static would completely drown out the signal. Thanks so much for joining me on this explainer, and I hope you walk away with a newfound appreciation for the quiet hardware actually keeping us all connected.